Okay, so in the previous video, we finished talking about how peptides are going to get fragmented and what an MS2 scan is going to look like. Now let's look at some real data, and we're going to start by talking about the MS1 scan. And in an MS1 scan, we're hoping to identify intact peptides. So that very slow liquid chromatography column is eluting peptides at 5 nanoliters per minute, and at one instant here is a spectrum of all the m over z's, all the mass charged particles that are coming off that column at that instant. This data acquisition might take around 100 milliseconds, so it's a very short snapshot. The next thing the mass spectrometer will do is the data acquisition software will quickly identify 5 of the largest peaks in a region of interest, so it's not counting anything below 500. Then it's just going to pick the large 5 peaks. And then it's going to, in turn, do MS2 spectra. So we'll first, on the first MS2 scan, we'll analyze the 511 peak. And the second MS2 scan will analyze the 570.7 peak, and so on. And this is why it's called tandem mass spectrometry, because again you're doing 2 different types of scans, or sometimes it's called LC-MS-MS. The first MS stands for MS1, the second MS stands for an MS2. And this slide emphasizes that these these peaks could be anything. We hope they're in different peptides that are eluting at the same time off the column, but they could be any charged particles, and there's also a lot of electrical noise here. But for the MS2, we're going to take all this material that's coming off the column at a particular instant, and we're going to throw away most of these ions. We're going to make the apply fields such that these orbits are unstable. They're going to smash against the inside of the walls of the mass spectrometer. Only the ion with a mass of around 571 will have a stable orbit. This peptide will then be fragmented. So we're just looking at this peptide now. It's going to be fragmented. We're going to get an MS2 scan, and we're going to identify this peptide that's eluting at 570.7 m over z units at a particular point in time. Now, each of these scans takes maybe 100 to 200 milliseconds, so you have in this data acquisition path 6 scans. This is going to happen in less than a second, and so this is going to be repeated over and over and over again, thousands of times over the course of a 2-hour gradient, and you'll be able to analyze a lot of peptides this way. The selection of 5 peaks is an arbitrary one, and it is related to the scan speed. Newer instruments can scan faster, and so you might pick the top 10 peaks or so to analyze. So now we have that red peptide on the previous slide that eluted at 570, or that had an m over z of 570.7, and what I've shown here is all the different ways this 9 amino acid peptide could be fragmented. Again, we're fragmenting at the peptide bond. So if we had this original peptide, we fragmented on the very edge, we're going to have a B1 and a Z8 in this case. And let's look very carefully at the B3 ion and the B4 ion, which I've indicated by stars here. If we look at what's going to be different between these two, we're going to see that the difference is this amino acid. So when we look at the m over z's, the difference between this m over z and that m over z is going to be the 4th amino acid. So in principle, this is not the way things are normally done, but because it's a little too complex a problem, but you could just take a slide rule or whatever and measure the distances between these various peaks, deduce the amino acids that are present, and then look at a database and see which proteins have those amino acids in that order. But that's a too complicated problem, and for instance, how would you know that it's this red peak goes to this red peak? You wouldn't know necessarily that you shouldn't be measuring that peak, or, this peak. But again, we can deal with that mathematically in other ways. So here's a little schematic of a mass spectrometer. We'll step through the process. Here we have our very small liquid chromatography column. Here we have an ion guide, some optics that's going to guide charged particles into the center of the mass spectrometer. This is the, in this type of mass spectrometer, it's called the ion trap, and it's going to be the mass analysis component where fields are applied and certain ions will survive. And this is a detector, so eventually it will leave the trap and go into the detector, and this will record a signal indicating the presence of a peptide. So here's what a mass spectrometer looks like. It's a benchtop instrument. We have pumps that are going to cause liquid to flow into the mass spectrometer right here. This is a sample pickup instrument called an auto sampler. This is going to load samples automatically. And underneath the mass spectrometer there are large vacuum pumps which are pumping down the insides of these instruments so that gas molecules are not present that you don't want to be for the peptides to collide into. So again, here's just the highlight. This is a column that has about 100 micron or maybe 75 micron inner diameter. It's placed very close to an inlet which is both charged and heated, and it's going to again inject peptides into elute from here at nanoliters per minute. It's going to inject peptides into the mass spectrometer. Here the peptides are being injected. They're being isolated. At first, all of them are being isolated in the ion trap, and they will all be released to the detector at the same time, and this is going to produce the MS1 scan. This is going to be the snapshot of all ions that are eluting off a column at a particular time. So 100 or 200 milliseconds have elapsed. We're going to keep, we're still eluting material from the column, and the assumption is that over the course of those 100 milliseconds nothing has changed, so the ions in the ion trap are the same as those that just went into the MS1 detector. But now, because we're going to do an MS2 scans, we're going to isolate only the one peptide that has a certain mass. All the other peptides have again, are not stable in the electric fields, and so they're gone. I want to emphasize, though, that it's not a single molecule. It's just a set of molecules, all which have that certain mass. It's probably several million molecules that have mass 570.7. Now we're going to introduce helium gas with high kinetic energy. These are going to collide like billiard balls into the peptides. It's going to cause fragmentation of the peptides, and they're going to fragment at all different peptide bonds, and so you're going to have a distribution of fragment sizes, and then you're going to have those B and Y ions enter into the detector, and that's going to produce an MS2 scan. And you might notice the different general appearances of the two scans. I'll back up for MS1. Here's the MS2. It's sort of this picket fence type appearance where you have a few peaks that are large and that they're generally spread out relatively regularly. That's because the distance between any of those two peaks is based on a single amino acid. Now I'll flip back to the MS1 scan. And here you can see a very different pattern. You have essentially an exponential decay in terms of intensities, a lot of noise present. There, in this case, there are a fair number of peaks that are there, but that's not always typical. But again, it looks very different than that picket fence type scans. This is an MS1, the other was an MS2. Okay, and so then after you've analyzed, since we're doing a top 5 type analysis, after you've analyzed peptide 1, then you would repeat the process with peptide 2. And so now what we've done is we've generated this raw scan. We have different M/Z intensities for different peptide fragments. And in the third video, we'll show how we get from a raw spectrum to an interpreted spectrum where we believe we know the amino acids that are present in the peptide that gave rise to that spectrum. Okay, thank you for listening.